In this video, after talking about measures of disease frequency, we will talk about how can we measure an association. So we talked about how to measure frequency of a disease, but now we come to more interesting questions such as what causes those diseases? How come some people have the disease and some people don't have them? In epidemiology, we ask many interesting questions such as does smoking cause lung cancer? Will poverty lead to obesity? Is low intelligence leading to suicide? Or do people with hypertension get Alzheimer's disease later in life? These are all questions for an association. An association has two main parts, an exposure and an outcome. The exposure is a potential cause of the disease, or a risk factor, or a protective factor. The outcome is usually the disease which interests us. Even though we would like to know what is the cause of diseases, in epidemiology we very often cannot find proof for causality. So we end up only with an association. So remember that association does not mean causation. We talk more about the differences between association and causation in the next lecture concerning assessment of epidemiological studies. To quantify an association, that means the relationship between an exposure and an outcome, we use either relative or absolute measures of association. Relative measures of association are risk ratio, incidence rate ratio, and odds ratio. Absolute measures of association are risk difference and incidence rate difference. In the previous lecture, we said that risk is actually another word for cumulative incidence. So risk ratio is the same as cumulative incidence ratio. Also, relative risk is another way how we can say risk ratio. Relative measures of association are always some ratios. You need to have two groups which you compare. Keep in mind that you study an association between an exposure, which is a risk factor or a potential cause, and an outcome, which is a disease of interest. So one group should be exposed to that risk factor, and the other group should be unexposed, so you can use it for comparison. Risk ratio is calculated the following way. In the numerator, there is a risk of the disease in the exposed group. In the denominator, there is a risk of the disease in the unexposed group. Risk is cumulative incidence that you already know how to calculate. In the previous video, we learned how to calculate the occurrence of the disease. Now, talking about measures of association, we do something more interesting. We ask what can cause the diseases. We will again use the example of the sleeping in the classroom disease. We will ask whether the students sleep in the classroom because their lecturer is boring. So we study an association between a boring lecturer and the sleeping in classroom disease. The boring lecturer is exposure, and the sleeping in classroom disease is the outcome in this association. To quantify an association, you have to have two groups which you compare. One group is exposed, and the other one is unexposed. We have two classrooms in this example. In classroom A, the students are exposed to the boring lecturer, so this is the exposed group. In classroom B, the students don't have the boring lecturer, so this is the unexposed group. We need to calculate this risk of the sleeping disease in both groups. In each classroom, there are 10 students. Nobody is asleep at the beginning at 9 a.m. In classroom A, 4 students are asleep at 10 a.m. So the risk of the disease, in other words, cumulative incidence of the disease, is 0.4 because it is 4 new cases out of 10. In classroom B, 2 students are asleep at 10. So the risk is 0.2 because it is 2 new cases out of 10. Now let's calculate the risk ratio for the association between the boring lecture and sleeping in classroom disease. In the numerator, there is the risk in the exposed group, which is 0.4. In the denominator, there is the risk in the unexposed group, which is 0.2. So the risk ratio is 2. Again, we need to specify the time point. So it is over an 1 hour period. What does this number mean? How do we interpret it? So if the risk ratio is equal to 1, it means that the risk among the exposed is equal to the risk among the unexposed. In other words, we can say that there is no association between the exposure and outcome. If the risk ratio is higher than 1, then the risk among the exposed is greater than the risk among the unexposed. So we conclude that the exposure is associated with an increased risk of the outcome. If the risk ratio is smaller than 1, then the risk among the exposed is lower than the risk among the unexposed. And we conclude that the exposure is associated with a decreased risk of the outcome. How do we interpret this measure of association between the boring lecture and sleeping in classroom disease? We can say that students exposed to the boring lecturer had twice the risk of sleeping compared to the unexposed students over an 1 hour period. We can also say that the students exposed to the boring lecturer had 100% higher risk of sleeping compared to the unexposed students over an 1 hour period. When we have a dynamic cohort and are able to calculate the person time, we choose to calculate incidence rate instead of risk. Thus, a measure of association in a dynamic cohort is incidence rate ratio. It is calculated the same way as the risk ratio. In the numerator, there is incidence rate in the exposed group. In the denominator, there is incidence rate in the unexposed group. In case control studies, we are not able to calculate risk ratio or incidence rate ratio. Instead, we choose to calculate odds ratio, which is counted the same way as the other two measures. In the numerator, there are odds in the exposed group, and in the denominator, there are odds in the unexposed group. Here is a small exercise for you. A study compares a new drug against cancer to an old drug. Odds ratio of adverse events of the new drug is 0.4 compared to the old drug. Which of the following is correct? A. There is no association of type of drug and adverse events. B. The new drug is associated with fewer adverse events. C. The new drug is associated with more adverse events. The odds ratio 0.4 is lower than 1. It means that the new drug needs to be associated with fewer adverse events. Now let's talk about how we can express an association in absolute measures. Absolute measures of association are risk difference and incidence rate difference. To calculate a risk difference, you need to know the same numbers as that you need to know for the risk ratio. You need to know what is the risk of the disease in the exposed group and risk of the disease in the unexposed group. However, you don't make a ratio, you make a subtraction. So risk difference is calculated as a risk in the exposed minus risk in the unexposed. Again, if you have a dynamic cohort and if you can calculate person time, you choose to calculate incidence rate difference, which is incidence rate in the exposed group minus incidence rate in the unexposed group. Let's look once more at the classroom A, which is exposed to the boring lecture, and classroom B, which is unexposed. The risk of the sleeping in classroom disease in the exposed classroom is 0.4. The risk in the unexposed is 0.2. So the risk difference is calculated as 0.4 minus 0.2, equals 0.2. What does that mean? If the risk difference equals 0, then we can say that the risk among the exposed is equal to the risk among the unexposed. In other words, there is no association between exposure and outcome. If the risk difference is greater than 0, then we say that the risk among the exposed is greater than the risk among the unexposed. In other words, the exposure is associated with an increased risk of the outcome. If the risk difference is lower than 0, then the risk among the exposed is lower than the risk among the unexposed. In other words, the exposure is associated with a decreased risk of the outcome. Specifically, what does the risk difference 0.2 means for an association between boring lecture and sleeping in classroom disease? We can interpret it this way. There was an 0.2, that means 20% excess risk of sleeping in those exposed to the boring lecture compared to those unexposed over an 1-hour period. In other words, we can also say there were 20 more cases per 100 people of sleeping in those exposed to the boring lecture compared to those unexposed over an 1-hour period. The relative and absolute measures of association are compatible with each other. They tell us a little bit of a different information. The relative measures inform us about the strength of an association. The absolute measures will inform us more about the impact of an association. Let's talk more about measures which will tell us about the potential impact of exposures on public health. One such measure is attributable risk. Imagine this scenario. The Ministry of Health should decide which of the following 2 interventions should be funded. The first intervention would be to replace a chemical substance that causes cancer with a safer one. The second intervention would be to completely remove a full additive that causes cancer. To do this on the nationwide population level would be very expensive. The budget is constrained and he can choose only one intervention. Which one will it be? In this case, it would be helpful to know the attributable risk. Attributable risk is a measure of public health impact of the exposure on the exposed people. It answers the question, if we remove the exposure, how much will the disease burden be reduced in exposed people? Attributable risk is essentially the risk difference or incidence rate difference. If we can assume causality between exposure and outcome, and if there is no bias. Let's come back to our example with the sleeping in classroom disease. We have already attempted to calculate the association between the boring lecture and the sleeping in classroom disease. We will now calculate the attributable risk, which will answer this question. If we remove the lecturer, how many cases of the sleeping disease will be prevented? We cannot blame the lecturer for all the sleeping, because look, 2 people are asleep in the classroom too as well, and there isn't the boring lecturer. Let's call this the background incidence. The incidence in the exposed group is the background incidence plus the incidence due to the boring lecture. Here, let's assume causality and no bias. The attributable risk is the same as the risk difference, so it is 0.2. It means that 20% of the risk of the disease in the exposed group can be attributed to the lecturer. Another measure strongly associated with attributable risk is number needed to treat. Number needed to treat is calculated as 1 divided by attributable risk. So in our case, the number needed to treat would be 1 divided by 0.2. It equals 5. How do we interpret this? The interpretation is that 5 people need to receive the intervention, that means staying away from the boring lecture, to prevent one case of the disease. The attributable risk can be also expressed as percentage. In this case, we call it attributable risk percent. It is calculated as follows. In the numerator, there is attributable risk, and in the denominator, there is the risk among the exposed. So in our case, the attributable risk percent would be calculated as 0.2, which is the attributable risk, divided by 0.4, because this is the risk of the disease among the exposed. It equals to 0.5, which is 50%. The interpretation is that 50% of the cases of sleeping among the exposed group could be prevented if we eliminated the boring lecture. So far, we talked about attributable risk, which only concerns the exposed group. So it can only tell us, if we remove the exposure, how many cases of diseases could be prevented among the exposed. But often, we are interested in the potential impact on the whole population. In this case, we calculate population attributable risk, which is the excess risk of a disease in the total study population that is attributable to the exposure. With total study population, I mean both exposed and unexposed people. Population attributable risk is calculated as follows. We multiply the attributable risk by the prevalence of exposure. We already know the attributable risk is 0.2. Now we only need to know the prevalence of exposure. The total study population are 20 students. 10 of them are exposed to the boring lecture. So the prevalence of exposure is 10 out of 20. That means 0.5. It's 50%. Let's calculate the population attributable risk. It's attributable risk 0.2 times prevalence of exposure 0.5. It equals 0.1. In other words, the population attributable risk is 10% over 1 hour period. So among the entire study population, an excess risk of 10% could be attributed to the boring lecture. Again, we can also calculate a measure called population attributable risk percent. This measure is calculated as follows. In the numerator, there is risk in the total population minus risk in the unexposed. And in the denominator, there is risk in the population. Population attributable risk percent tells us what is the proportion of the disease in the population that could be prevented by eliminating the exposure. To calculate the population attributable risk percent, we need to know two numbers, risk in the population and risk in the unexposed. The risk in the population would be 6, because it's 6 new cases in the whole population, out of 20, because there are 20 students in the whole population. It equals 0.3. The risk in the unexposed would be 2, because there are 2 new cases in the unexposed group, out of 10, because the population of one classroom is 10 students. So it equals 0.2. So let's calculate the population attributable risk percent in our example. So in the numerator, there would be 0.3, because this is the risk in the population, minus 0.2, because this is the risk in the unexposed. In the denominator, there would be 0.3. This equals to 33%. The interpretation is that 33% of all the cases of sleeping could be prevented if we removed the boring lecture. A big attributable risk does not necessarily mean a big population attributable risk. population attributable risk depends on both the strength of the association and the prevalence of the exposure. So we will have a large impact on the population if the association between the exposure and the outcome is strong, and also if the risk factor is common. Let's compare two different examples. In the first example, the strength of the association between exposure and outcome is high. It's measured with relative risk, which is 10. So that's a very strong association. The exposure is rare. The prevalence of exposure is only 0.005. The attributable risk is very high, it's 90%, but the population attributable risk is low. It's just above 4%. So because the exposure is so rare, we will not have a very large impact on the whole population if we removed it. In the second case, we have again a relative risk, 10, which is a strong association between exposure and the disease. But the exposure is quite common. The prevalence of exposure is 0.5. The attributable risk is 90%. And here we can see that even the population attributable risk is very high, is above 80%. So because the exposure is more common, if we remove it, we will have a higher impact on the whole population. In the end, let's summarize the basic measures in epidemiology. So first, we need to measure how frequently diseases occur. We measure this with incidence or prevalence. More specifically, incidence we express either as cumulative incidence, in other words, we can say risk, or as incidence rate. Cumulative incidence, aka risk, we use for closed cohorts. Incidence rate we use for dynamic cohorts. Prevalence can be also expressed with odds. An association can be measured with relative measures or absolute measures. The relative measures are risk ratio, incidence rate ratio, or odds ratio. The absolute measures are risk difference or incidence rate difference. To measure potential impact, we either express the impact of exposure on the exposed group. In this case, we use attributable risk or attributable risk percent, or we measure the impact of exposure on the whole population. In this case, we use population attributable risk or population attributable risk percent.